Hello, everyone. I see people are still joining, but I do want to get started on time today because it's a pretty short webinar, just a 30-minute webinar today. So I want to thank everyone so much for coming and joining me today. My name is Amber Brown. I'm sure not all of you know me. I'm the North American Sales Director for Move Solutions. Today, we will be doing a webinar, which is actually going to be the first webinar in a series of webinars that I will be having. And the first one is Monitoring 101. So I really wanted to start with just the basics of what is structural health monitoring, why should we be monitoring infrastructure, how can we monitor it, and the different ways to monitor it. So I wanted to really break down the basics. Some of you may know all of this information, but I think it will be good to kind of build on this webinar for the future webinars. So who is Move Solutions? Some of you may know, some of you may be new. So we are the global leader in dynamic wireless monitoring solutions. So our company was founded in Italy about 5 years ago. And the founder and CEO, Ferdinando, was actually in college at the time, and he was working with a company, and together they saw that there was going to be a huge problem with, in that time, bridges, with failing bridges, and with infrastructure in general, because we are at that time, and not just in Europe, but all over the world, where infrastructure is aging, it's old. Materials that were used many, many years ago are at the end of their lives. Some of them were intended to last longer and they're not. Some are just at the end of their lives. So they saw a problem. And during that time, our founder actually patented a technology on one of our sensors called the DEX sensor, specifically to monitor bridges and the health and safety of a bridge dynamically. At that time, it's mainly static monitoring that you hear about to monitor infrastructure. So he really wanted to dive deeply into the dynamic side of monitoring. After he, patented the technology and made the sensor, 6 months later, the Morandi Bridge in Italy actually went down. It was a huge tragedy. A lot of people died. And so it kind of started to raise a lot of awareness of how important it is to monitor infrastructure at that time in Europe. But as we're seeing, so on the left-hand side, you can see all of the areas that we are in now. So we have been growing very rapidly globally because every country has the same problem. I know just in the US, if you think about, the past few years, we've had just tons of infrastructure problems. We have had the FIU bridge collapse, which is actually where I went to school. We had the Pittsburgh bridge collapse, which is where I live. We had the building collapse in Miami, which was a horrific scene. Last week, there was a train derailment in Washington. There was the overpass collapse in Mexico recently. So it's a global problem, and it's something that we have worked really hard in trying to solve and coming up with sensors that are all wireless, easy to use. We have advanced algorithms to understand the data that you receive from the sensors to make it as easy and cost-effective as possible to monitor infrastructure and make it scalable. There shouldn't be a lack of resources to monitor because you're able to scale our sensors. You can start small and build on to monitor as many structures as you need to. So first, I'm going to start with what is structural health monitoring. I always fall into the trap where I assume everyone that I'm talking to actually knows what structural health monitoring is. But I've actually been asked this question a few times in the past few months with different meetings where they stop me and they say, but what actually is it? And structural health monitoring is the process of implementing a damage identification strategy. So here the damage is defined as changes to the material or geometric properties. So it's understanding the structure, from a dynamic and static point of view and understanding if there is damage, if there's changes in the structure that will be causing damage, and what is causing the damage. Is it environmental factors? Is it settlement problems? There's a million different reasons that there could be damage happening. So it's really just following the life of that structure and understanding how long is the structure going to last. Is it at the end of its life? Do we just need to perform some maintenance to, get many more years out of it? And the typical reasons for structural health monitoring. So there are many reasons to monitor infrastructure, but to kind of just break them down. So one of the reasons is to improve maintenance and inspection. So detecting the damage in early stages, enabling a proactive response, and optimizing that maintenance process. It's always easier to fix the bridge before the damage or any structure, buildings, dams, tunnels, any of those structures. It's much easier to fix the problem before it's completely broken, before you have to start replacing structures or shutting them down. And then with the fatigue monitoring and lifetime prediction, so you can boost the lifetime and safety of the structure and support the cost-effective solutions for that structure. It gives you the continuous observation and data of the structure and just gives you better insights and better product development. There may be a new material that you start using on the structure and you find that actually it's not lasting as long as it was intended to do so. So there's a lot of different reasons, to actually monitor, not just for safety, but also for cost reasons. And also identifying a critical situation. So you can take the immediate action that you need to take to avoid, a collapse or the really significant damage. You can save lives and avoid the breakdown. And, also on the other side of it, you can save a lot of money. It's a lot of tax dollars and a lot of money is going into this infrastructure that has failed or is so close to failing, when we could have just monitored it and understood that it needed the maintenance it should have had years ago. And the monitoring challenges. So at Move Solutions, we've really tried to look at all of the challenges that everyone has with monitoring. Typically, if you want to dynamically monitor a structure, it's a very expensive cabled system. It takes tons and tons of hours to install, very, very costly. You have to shut down traffic for days, or shut down buildings for days. It's not an easy task. So we've really looked at the challenges and have tried to solve all of the challenges that we could solve. And some of the challenges are that you need reliable data, high signal quality, long-term stability and durability, and extraction of the essential information needed for the immediate reactions, maintenance decisions, and the prediction of structural lifetime. There is an endless amount of data that you can get from infrastructure with monitoring, but we've worked really hard on advancing our algorithms and understanding and giving you the tools to understand the data that you are receiving from these structures. So you're not just receiving endless amounts of data that you have to sort through and have the manpower to have manual algorithms and understand what's going on. It's easy because we have those tools for you, which makes it just, you can set alarms and you can not look at it again. And when a threshold is surpassed, you get an alarm on your phone or on your computer, or on your iPad. And typical constraints were size of the structure with long distances. As I mentioned, with the cabled systems, it's very expensive and hard to monitor long distances. With the wireless sensors, it's easy. You can simply just install them at certain increments. You can cover hundreds of feet of structure, with half a day of work. The sensor installation environment, so the space, accessibility, weather, working positions. With our sensors, they're very easy to install. So it's not too hard, to reach out of a building and put a sensor on the side of the building. It's very simple. You can glue it on, you can bolt it on. And then the adverse environmental conditions, you need a system that can work in heavy rain, in the desert, in really harsh environments, really hot temperatures, really cold temperatures. And then also with the data connectivity, you may be in a remote location that has not a lot of cellular service. And because we use the LoRaWAN communication system, you get a very long range, and it works well with situations where you have not a lot of data available and not a lot of cellular service. And if you have none, we do have the option to connect an Ethernet cable if you need to. And then the data transfer and data management and storage. So we actually package our data and send it through the communication system and then unpackage it. So that gives us the ability to send these large amounts of data without using a ton of energy and draining our batteries. So that gives us the possibility of having a really long battery life of 2 years up to 8 years of battery life, because we have such a good way of transferring that data. And then with the data management and storage, we have our cloud platform, as I mentioned, which makes it really easy to understand the data, manage it, and then you can also download all of the data and save it forever. So the monitoring types overview. So I keep talking about dynamic monitoring. So there's two main categories. There's the static monitoring and the dynamic monitoring. And understanding the difference between these two types of monitoring is what is really important, because most of the monitoring systems you come across, especially the wireless, are static monitoring. And those are monitoring the static parameters such as displacements, deformations, rotations. You can monitor, if cracks are opening or something that's evolving slowly over time. It's easily manageable and an interpretable amount of data. So those are the systems you typically come across. What we specialize in dynamic monitoring is monitoring the dynamic parameters such as frequencies and modes of vibrations, etc. And this gives you the opportunity to record occurrences slowly over time and see how that structure is acting over time before you actually have that real physical change. This amount of data is a lot more difficult to manage and interpret. So we've really focused on this to make it as easy as possible to understand this dynamic monitoring. So I always like to show this. Some of you may have seen it before, but it's a really good way to understand the difference between static and dynamic, because it's hard to understand the value in our system if you don't understand the difference between static and dynamic monitoring. So I always like to use the example of a car. So if you're driving in your car and your car alerts you that there's a dent in the side of it, that would be a static change. So it's a visible change that you can see. I mean, you can't always see a static change if we're talking about, a few degrees difference in a structure, but this would be, pointing a total station at the vehicle, and then it says, hey, there's been a change or the structure. So in this example, the car has a dent and you see the change, there's a change, but then you have to work backwards. So you have to understand what caused the change in the structure, or in this case, the car. So you have to understand, if something hit you, did you hit something, what caused this change in the car? So you have to, you find the problem, and then you work backwards with an investigation to find out, what caused that problem. With dynamic monitoring, you're actually monitoring the behavior and state. So in this example, you would be watching the driver. So maybe that driver is talking on the cell phone, drinking a cup of coffee, and steering with their knee, and they swerve off and they hit a lamppost. Well, then you understand that because they hit the lamppost, there's a dent in the side of their car. So with our monitoring, we're monitoring the behavior and state. So we're monitoring the vibrations and accelerations and understanding if there's a change in the structure before you actually would pick it up on, say, a total station, or if you have a tilt meter on the structure, you're able to understand that there's a change happening in that structure before you start to see that physical damage. And that is the real value in Move Solutions, because we can take all of those predictive indicators and really prioritize the resources, focus the investigation, and reduce the overall cost. Because, as I mentioned before, fixing something as soon as you know there's a problem is way more cost effective, way safer than fixing something after you can visibly see that severe damage. I've been under bridges in Pittsburgh where they have tarps set up because there's pieces falling off of that bridge. So it's all about, prioritizing the resources and really, taking that immediate action when it's needed. So there's two main types of monitoring, and you can do one, the other, or both. So there's real-time monitoring with the peak analysis. So that is recording 24/7, understanding the structure if there's some sort of anomaly happening. So you can set the thresholds, and if something happens instantly, you're alerted to it. So say you are monitoring a post-tension bridge and one of those cables breaks. You're going to see that immediate response that the structure has changed and then immediately get alerted. And then there's the long-term monitoring. So this is understanding how that structure is acting over time using, various algorithms such as OMA, and then also with the modal analysis. So this is really great for bridges, buildings, any type of large infrastructure like that you really need to understand the modal analysis of and understand how, it's reacting in the long term. So getting into the applications, and I'm going to start talking a little faster. I think I'm talking too much. We have four main categories. I mean, we're constantly finding new applications, almost daily, but the four main categories is infrastructure, bridges, viaducts, culverts, dams, tunnels, construction sites, vertical structures, the railway industry, and then geotechnical. So first, I want to talk about bridge monitoring. I'm not going to talk about every type of infrastructure monitoring because in my next webinars, I want to kind of focus in on each application and talk about them in more detail. But with bridge monitoring, I mean, I know, as I mentioned, we have a lot of problems with bridges around the world. We're getting a ton of inquiries and monitoring a lot of bridges, especially in North America and the United States, because they're complicated. They're complicated to monitor and they're aging. There's been poor maintenance on them. So a lot of the bridges already have problems. And some of the parameters that are important to monitor on bridges and that we can monitor are the dynamic parameters, as I mentioned. So the acceleration and the dynamic displacement of a bridge. The static parameters, so that would be the inclinations or static displacements. The modal parameters, which are the frequencies, shapes, and damping of the bridge. And then the environmental and geotechnical parameters. We have the air temperature, the wind, the humidity. We have settlements, groundwater. There's a lot of other factors that go into monitoring the structure. It's not just about the structure, but we try to work towards what is causing the change in the structure. So a lot of the times looking at the environmental and the geotechnical parameters, we're able to do so. Next, we have construction site monitoring. So this is something that, especially in North America, is growing in popularity. So I know there are certain regions that you have to monitor for vibrations if you're performing construction. There's other regions that maybe you're recommended to do it, but you don't have to do it. But it's growing in popularity because it's easy to monitor the vibrations caused by your construction. We have a small sensor called the vibrometer. It's a PPV vibrometer, so it measures the peak particle velocity, which is basically just the ground vibrations that are caused from the construction that you're performing. So a great tool and something we're seeing a lot of construction companies doing right now is just adding these vibrometers onto their construction sites. They're very low cost. They're a wireless, they're like this big, small sensor that you can put on surrounding structures so that you're not causing damage to them. And also it's a way to prove that you have not caused damage to it. We live in a very litigious world where a lot of people like to place blame. You may be doing construction on a building that's next to a building that's 80 years old and they haven't performed any maintenance on that building. And then 3 years down the road, they say, well, we have all of these cracks in our foundation, and I think it's from that construction. So this is a great tool to monitor your vibrations. You can keep the data forever. And it's a good way to back up that you did not cause damage because you've been within, the guidelines for vibrations. And it's just a way to protect yourself and the structures around you. So here's an example of, a way we would monitor a construction site. So in this case, with the shoring piles, we would want to monitor those to make sure they're not moving. We can use our static sensor, which is our tilt meter, to make sure those piles are staying where they should be staying. And then the green dots on that building are the vibrometers. So making sure that this construction that you're performing so close to that building is not going to have an effect on that building structure. And then we have the vertical structures, so buildings. As I mentioned, in Miami with the building collapse, it's a big problem. And we've had a lot of people asking now to monitor their old buildings, especially with the construction sites, as I mentioned, being very aware of the buildings around them. So we can monitor them not just for vibrations, but we can also perform that modal analysis that I was talking about earlier that we can do on the bridges. We can perform the same modal analysis on a building. So you can see over time, something is starting to shift within that building and understanding, what's going on with it. So maybe it's an environmental factor, perhaps there was an earthquake, and then after the earthquake, you see that the building has shifted a bit and moved. There's a lot of ways to monitor the buildings. And I think that I know building monitoring is very common on the West Coast with all of the earthquakes, but it's also becoming common, all around the country. And then we have railway monitoring. So there are, different things to monitor on the rail tracks. There was just the train derailment in Washington last week. It's a common problem. It's very expensive when you have these train derailments. It holds up traffic. Luckily that train derailment was just grain, but trains carry, very toxic chemicals, things that can explode. So it's very important to make sure you have a safe track. So things that we can monitor would be the cant, which is, if the tie is moving this way, the twist, if you have one tie moving this way, one moving this way, and you have a twist of the track, the vertical deflection. So perhaps one side of the track is starting to sink, and ballast void. So we can actually dynamically monitor the rail track as well. So we can use our dynamic sensor to understand if there's a void forming under that track before you actually have the track, falling into a hole. And then the geotechnical monitoring. So with the geotechnical monitoring, it's not just the track you have to worry about. In most cases, you're worried about what's around the track. So do you have a large embankment of soil? So you can measure that to make sure that the slope is not changing. Do you have a large rock embankment? And then you can understand the groundwater level. So there's so many geotechnical parameters that you can monitor, as well as the track itself. And this is just the overview of the geotechnical monitoring, that we can do with all of these categories. And, the three main categories are the soil, hydro, and weather. So I'm going to talk 1 minute on, I have 3 case studies, but I'll just talk about the Colosseum. So I have some case studies. For example, the Colosseum in Rome, we're actually using our sensors to monitor. They actually painted the sensors so that they're aesthetically pleasing and you don't see these sensors on that beautiful old structure. But what they're doing is they're performing construction on the metro under the city, and they want to make sure that, the Colosseum is staying the way it should stay. So they're using dynamic and static sensors to understand, if that structure is moving, and make sure that it doesn't. So I'm just going to go to questions because we have 5 minutes and I want to make sure that I can answer everyone's questions. I have one of my colleagues here to help too. So if you see me looking at my phone, it's because he's helping me with questions. I'm trying to click on it. There we go. Okay, so yeah, for your modal analysis using accelerometers, what is the accuracy of time synchronization, timestamp between sensors? So it is, I'm not sure, I want to say 60 microseconds, 50 microseconds. For your construction vibration monitoring, do your performance specifications meet the requirements for USBM criteria for detection of building damage? Yes, so we work with the RI 8507 standard in North America, and we do not work to the ISEE standard, but that's for drilling and blasting. We work to the standard for building damage. So it's the RI 8507 standard. You can also set the vibrometer into custom mode as well. So if you have, a specific job where you're monitoring maybe something that, if you're monitoring a hospital and you want to make sure, the equipment is not being affected by vibrations, then you can set, the standard much lower in that threshold. So you also have the working custom mode as well. Do you have the 923 MHz LoRa frequency? I'm not sure, but let me find out for you. I'm waiting on that answer. Which type of parameter will be measured in strain gauge monitoring? Suppose if we are monitoring in real time and once a day, which type of parameter? One moment. Which type of parameter will be measured in strain gauge monitoring? Suppose if we are monitoring in real time and once a day. So if we're monitoring once a day with strain gauge, let me ask. And the highest sampling rate from the sensors. He's typing. Oh, static, dynamic, or both for the strain gauges. Okay, he's answering me in order. Okay, so Richard, how do you offset the impact of battery life with dynamic monitoring? Okay, so with the dynamic monitoring, it does, I'm finding out the highest sampling rate, but I know with the dynamic monitoring, it's at least 2 years of battery life. So that's if you're doing the maximum sampling rate every day. So if you're doing that maximum sampling rate, then you get around 2 years of battery life. And then if you drop it down, then, you get more battery life. So you do get at least 2 years. If you're doing the highest sampling, then you don't get, up to 8 years. And then the frequency for the US is 902 MHz for the LoRa. That's one question. And then with the strain gauge, I believe the answer, okay, you can't see the questions. I guess I can only see the questions. 1 second. So with the strain gauge monitoring, so right now we have our analog node, which is a static node, which can be connected to the strain gauge. But we're actually putting out a dynamic node as well at the end of June. So we'll be able to do both to answer that question. And then let me find out the maximum sampling rate. And let me make sure I didn't miss any other questions. Okay, I answered the frequency. So it's 640 hertz on accelerometers. And do we have a vibrating wire sensor node? So we have the analog and digital nodes, which we can connect the vibrating wires to. And then that allows them to be integrated into our system. Okay, and then I see there are some hands raised, but I actually don't know. And then if we're talking about the sampling rate and cadence, we can have up to 1 synchronized acquisition per hour with the synchronized samplings. Okay. Yep, I think I answered that, Richard. So there's the trigger mode. So, it will be if the threshold is surpassed. And then with the cadence, if you are doing the synchronized acquisitions, you can do up to 1 per hour. But you can obviously drop that down too. So you don't have to do 1 per hour. Thomas, with the accelerometers at 640 Hertz, you'd be around the 2 years in the battery life. Okay, I think I answered everyone's questions. If I missed one, please drop it down. I see some hands are raised, but to be honest, I absolutely have no idea how to see whose hands are raised. So if you're waiting for me to call on you, just drop it in the chat because I'm just really missing that there. Okay, I think there are no more questions. Feel free to email. There's info@movesolutions.it, or you can find me on LinkedIn and reach out. And also, if you have any feedback or if you have any specific topics you want to see in the next webinars, let me know. If you have, a specific scenario or project that you're wondering if you should, monitor or how to monitor, let me know. We can book a meeting or have a phone call. So I appreciate everyone's time so much. Thank you so much.